So let me just briefly recap what the Heisenberg picture is about, and then I want to come back to discussing the higher dimensional version of the harmonic oscillator. Again, there's an application of rotational symmetry, as we will see. But first, so remember, the Heisenberg picture is not a different formulation of quantum mechanics. It's really just a change of basis on how you describe your operators and your states, right? So always remember that symbol for symbol, the expectation value of any operator in the Schrodinger picture must be equal to the expectation value for the same operator but written in the Heisenberg picture. So this is the key conversion to remember. So this is Schrodinger, and this is Heisenberg. And so the key point is to recognize that the physical states evolve in time in the Schrodinger picture. In the Heisenberg picture, they do not evolve in time. Actually, let me just say that we always assume that H is time independent. Okay, this is to make it easier. It does get more complicated when your Hamiltonian depends on time. So, for example, in cosmology, this is one example. So people nowadays, they are interested in applying quantum mechanics to cosmology, mainly because of the very, very early universe. And so that is one place where the application of quantum mechanics would require that you think about Hamiltonians that do depend on time, because the universe is expanding. So necessarily the Hamiltonian of physics happening in expanding universe is necessarily time dependent, except for very, very special cases, it should depend on time. But for now, we're going to just focus on the case where H is time independent. But the eigenstates of time independent observables, in the Schrodinger picture, they do not evolve in time. Whereas in the Heisenberg picture, they actually anti-evolve. Okay, so anti-time evolution. And then the operators themselves if A does not depend on time, then they do not evolve in time. But this guy would involve, in fact, this is in fact often the crucial point here. The Heisenberg picture operator will be sandwiched between, will be gotten from taking the Schrodinger picture operator and then sandwiching it between the evolution operator and the anti-evolution operator. Right, U and U dagger. That's why this guy together with this guy is why I say you should just think of going between Schrodinger and Heisenberg as just a change of basis. Okay, just change of basis. And all of this you have to define. So let me put it as an important footnote. you need to define an arbitrary time, but you do have to write it down what it is. So T naught is what I call it, and this is the time where Schrodinger equals to Heisenberg time. Okay. So for example, U will be written in terms of e to the minus IH, and then T minus T naught. And T naught is the time where U is 1. And that's how you see that Heisenberg equals to Schrodinger for the operators. Yeah. Okay. So, as we've done already, we use this fact to offer a different perspective of how to solve the harmonic oscillator, right? So you can try to, so what we did was we got the position and the momentum operator in terms of the Schrodinger picture operators as a function of time, but you can try to do it for other operators and see how that could also allow you to solve other problems. What kind of operators you need depend on what kind of problems you're trying to solve. Okay. So that's the summary of. So what I'd like to do is I'd like to come back to the harmonic oscillator again, but now let's extend this to higher dimensions. Okay. So So for the most part, of course, we're interested in the three-dimensional case, but for some of the discussion, we don't really need to specify the number of dimensions. So what I'm going to do is I'm going to just write down that my Hamiltonian is 1/2 p squared, but now p squared is summed over all the squares of all the components in the different dimensions, plus omega squared over 2 and x squared. Okay. So by writing this, this guarantees spherical symmetry, right? So V is spherically symmetric. Of course, you can write down omega 1 for the first direction, omega 2 for the second direction, and omega 3 for the third dimension, right? So you can have a simple harmonic oscillator that is that has different frequencies in different in the different directions, and that's perfectly okay, and actually perfectly solvable as well. But like I said, I want to do this as an application of three-dimensional rotational symmetry, right? And you will again see how the spherical harmonics will show up. Actually, what we're going to do is the first approach is to simply use separation of variables. Which you guys have seen, I believe already. We talked about this even in the context of solving for the spherical harmonics themselves. We split the answer into theta part and the phi part, and that allows us to solve YLM. But here, the separation of variables is in the different Cartesian directions. Oh yeah, I just fixed a mistake in my notes. So in your homework, you're going to solve so in your homework, let me just write it down, and then I'll tell you what mistake I made. So in your homework, you're going to solve the one-dimensional case exactly. So what you're going to do is you're going to find out that the nth energy eigenstate wave function of the one-dimensional harmonic oscillator is equals to the Gaussian, which is omega over pi to the 4th root power times e to the minus omega over 2 x squared. Okay, so that's the ground state. But when you have an excited state, you will discover that this is multiplied by hn, which is the Hermite polynomials, times the square root of omega times x. The whole thing divided by 2 to the n over 2. Okay, so what I got wrong was the normalization factor. I think I accidentally included the some of the factors from this guy. Actually, let me make sure I get it right. Yeah, anyway, so it's what it is. I think that's correct now. I don't know why I had all this bunch of factorials and all these funny things going on there, but it's not quite right. Yeah. Okay, so so in the homework you will solve for the Hermite polynomials, and you will discover that it shows up in the harmonic oscillator problem. So in fact, by separation of variables, you can probably guess in the d greater than 1 case, you can actually guess right away what the wave functions are, right? So the wave functions for arbitrary states, but now will be labeled by 1n for each direction. So remember, n is an integer running from 0 to infinity, is for the x direction. So you have n1 for the first direction, n2 for the first direction, second, and n3 for the third direction. And so then the excited states would just be basically a product of all of these guys, right? So in fact, let me do it until nd. If you have d dimensions, and this would tell you that the wave functions would just be omega over pi, and then d over 4 e to the minus omega over x2. Now x squared, if you want, I can write it as r squared. And then this guy is the one that has, and then let me pull this out first. So this is, well, okay, let me write it down. So h and 1 of square root omega x1 divided by 2 and 1 over 2, and then multiplied by the second direction. So the second direction also contributes to this guy, but we'll have h and 1 and 2 here, square root omega x2 divided by 2 to the n2 over 2, and then you keep multiplying until you get the d direction where you have h and d of square root omega x to the d over 2 to the nd over 2. Okay. So that's in fact the wave function, and you know it will work right away. Why? Because the Hamiltonian is, in fact, split. It's a sum of all the individual Hamiltonians in each direction, right? They don't talk to each other basically. Okay, so when you sum over the individual Hamiltonians and you act it on this guy, so basically 1/2 pi squared plus omega over 2 xi squared without summing over I applied to n1 through nd is going to spit out omega times ni plus 1/2 n1 through nd. Okay, so basically you can see that right away, because why? Because this guy is going to be acting on the ith component of this wave function, and the rest of the components, the rest of the factors showing up in this product doesn't take part in the differentiation. So you can see right away that it's just going to give you kind of like the energy in each direction, so to speak. It's not completely accurate, but in terms of the technical calculation, it is basically energy in each direction, right? But physically, of course, the total energy is just a sum of all of that. And so once you recognize this fact, you can see that the total energy, the nth energy state is actually given by omega, and then n1 plus n2 plus n3 all the way to nd plus 1/2 plus 1/2 plus 1/2 d times, so it will be d over 2. Okay. And in particular, what that tells you is that the nth energy state is actually is labeled by the sum of all these integers, n1 to nd. Right? And so in particular in 3D, the 3D case is of course the most important. In that case, you would have the energy eigenstates are just given by omega times n1 plus n2 plus n3 plus 3 over 2, okay? And then the eigenstates are just these guys, but d is 3, right? So I don't think I need to write that down. But this is where there's a lot of degeneracy, as you guys can see. n1 plus n2 plus n3 will just give you one integer. And so for a fixed integer, let's say you pick an energy state, right, E10 or E22, well, there are many ways to write down n1, n2, n3 and sum them up in a way that gives you 23, right? N1 plus, yeah, there are many ways to sum 3 integers to give you let me just write it down. So for fixed n, there are many ways that are usually, actually let's see, let n, for fixed n, yeah, okay, let me just write it down. For fixed n, there are often more than one combination of n1, n2, n3 that satisfies n1 plus n2 plus n3 equals to n. Okay, so i.e. there's a lot of degeneracy. B or A or whatever. But anyway, there's a lot of degeneracy. So that prompts us to ask, right, how do we classify this degeneracy properly? And this is why I talk about it, because it's related to spherical symmetry. So what we want to recognize is that what we want to recognize is that remember that there are different ways of writing the Hermit polynomial as well, right? And so one of the things that we have to remember is that there is a raising and lowering operator method, and that in turn applies even for this case of higher dimensions, right? So what remember? So let's write down. So what we have to remember is that the excited states is given by, in fact, omega over pi to the 3/2 over square root of n1 factorial, n2 factorial, n3 factorial. And now I'm writing it in terms of the raising operator. So what is it? It's actually minus I dx1. Actually, let's write it as the following. It's minus I to the third power. Actually, it's n1 plus n2 plus n3 divided by minus I over square root of 2 omega to the n1 plus n2 plus n3. And then you have dx or d1 minus omega x1 and 1 d2 minus omega x2 and 2 and d3 minus omega x3 and 3, all acting on the Gaussian e to the minus omega over 2 and then x squared. Okay, x squared means x1 squared plus x2 squared plus x3 squared. Okay, so I won't repeat the argument again, but remember that for the one-dimensional case, you just have one raising operator acting on one Gaussian. Okay, but now you have 3 dimensions, so you have one set of raising operators acting on one Gaussian. Right? This is really 3 Gaussians multiplied together. The first direction, second direction, third direction, all multiplied together. So this guy is acting on only the first, and this guy is only acting on the second, and this guy is acting on the third coordinates of the Gaussian. And so what is important to remember is that these guys will differentiate the Gaussian and give you polynomials, right? And so, of course, the exact answer is here, but then you have to remember what these guys are. But but all we want to now observe is the following: is that this will give you n1 polynomial, or rather polynomial of degree n1 in x1. Why is that so? Because this will differentiate this n1 times, but each time it differentiates this, it will bring down 1 power of x1. Right? Of course, it's complicated. You have to carry out the derivatives, And there's lots of terms to worry about. But essentially, you can see that at most, when you differentiate the Gaussian ones, you get 1 power of x1. And anyway, this guy also gives you 1 power of x1. So you'll get at most n1 powers of x1 when you differentiate the Gaussian. From here, you will get n2 powers of x2, and then you get n3 powers of x3. Okay, so altogether, you get a polynomial of degree. So this will be a polynomial of degree r to the n1 plus n2 plus n3. So I'm just looking at, if you convert it to spherical coordinates and use the variable r, you'll see the highest power of r that you will get is just simply given by n1 plus n2 plus n3, right? Which also, by the way, happens to be the degree of the energy level, the label of the energy level. So that gives us a clue, okay, regarding what to do. Okay. So let me erase this first and then talk about what to do. Any questions for me at this point? You have a question for me?
What is sign in the Z without poly of degree?
Polynomial of degree r to the n1 plus n2 plus n3.
This is R.
R. Maybe my handwriting is not very good. Let me do it again. R. Okay? And so remember, R is just the radial coordinate in spherical coordinates. Okay? Yeah, so in fact, let's back up a little bit and think about it a bit slightly more abstractly. Okay, so I hope it's clear that H is spherically symmetric. Right? So let me just write it down again. H is p squared plus omega squared over 2 x squared. Okay, and so you can see that, of course, remember that under rotations. Remember that under rotations, P and X both transform as a vector, right? In fact, next semester we'll talk even more about this stuff. But basically, when you change your basis under the representation of the appropriate representation of the rotation group, you will get that P itself will transform like a rotation, will transform like a rotation under a vector. And then if you do that for the position operator, same thing happens. Okay. So R hat here is a matrix, but P and X are operators, right? So what I mean by here is that it just means that the components of these P over here and the RP over here these components. Now, because of that, you can see quite clearly, quite easily actually, that the Hamiltonian must therefore be a rotational scalar, right? Actually, let's do it for once, right? So this will give you D dagger, and then P A D dagger. This is 1. This is 1. So I can split up P squared into PA, but I can insert a DD dagger over here, and then D here. And why do I do that? Because D dagger PD, dagger PD is just going to do exactly what I said over here, plus 1/2 omega squared D dagger X A, again D dagger XA, D, same argument here. It's going to give you now 1/2, and remember this guy gives you R hat A, and then R hat A, let's say B, TB, and then this guy gives you R hat A, C, PC. Okay, so it rotates this, plus, same thing here, 1/2 R hat AB, XB, R hat AC, XC. So in this case, it's probably just easier to write it as matrix notation, right? So this is P, and then you have R hat transpose R hat T, and then this is 1/2 omega squared X dotted into R hat transpose R hat X. Okay, and this, you should notice, is of course nothing but identity, because the rotation matrices are translationally orthogonal. So it's 1/2 P squared plus omega squared over 2 X squared. Okay. And also, it's worth pointing out something that we don't talk about as much, but another symmetry operation is important, is parity. Okay, so what I'm going to define parity, as many books do, is that parity is an operator best thought about firstly as how it acts on the position eigencats. Okay, so parity which unfortunately I'm going to call P as well. It's the same as momentum. So maybe what I should do is give it a slightly different symbol, right? Yeah, okay, maybe I'll put a check on top of it, okay? So what it means is that is an operator that when you act on the position eigencat, will give you basically minus x. Okay. So because that's quite obvious, so I will just go ahead and do it twice. So what do I do? What does that give me? So this gives me that this is actually equals to P hat, P check, and then minus x, and then I'll do it again, so it gives me plus x. Right? So in other words, P squared is actually just the identity, which means that P inverse is actually just P, and actually this tells you that this also tells you that P is unitary, because why? Because we can do the following, right? So if you do for example, minus x prime minus x. Okay, this is now delta function, as we know, of minus x prime minus x. Okay, but the overall sign doesn't matter. Right? So there's a property of the delta function that you just want the argument to be 0. But if the argument is 0, it doesn't matter what the sign, overall sign is. So this is just delta function of x prime minus x. And this is actually equals to x prime x. Okay? But this guy is in fact x prime with the parity operator applied to it. This guy is also the parity operator acting on this. And so, in fact, that tells you that P dagger P must be identity. So P dagger is in fact P inverse, which is actually itself because of this. Okay. So what you can do is that from this alone, you can see that P, a change of basis induced by P, is going to just flip the sign of your momentum and position operator, right? Because these are genuine vectors. Okay, so the way you should be from here, you can convince yourself that the momentum operators. I should write out some homework problems for this stuff actually. But anyway, let me just tell you that you will, from the position eigenket, you can go to the momentum basis and you can convince yourself that if this is true, it has to be true that this will just flip the sign of the momentum. Okay? So this will follow from here. Okay? And so that tells you, this will tell you actually that P with the X sandwiched in between, this operator will just flip sign. Okay? From here you can prove this easily. And from here you get here, and then this will in turn tell you that the momentum operator will also flip sign under parity. Okay? So why am I saying all this? Because the Hamiltonian is in fact parity invariant as well. So from this and this, you can tell that the Hamiltonian is parity invariant. So let's collect what the facts are. The Hamiltonian is rotationally invariant and parity invariant. So therefore, we should be able to now identify the following compatible observables. Right? Is H, the Hamiltonian, is rotationally symmetric. So right away we know J squared is compatible. J3 must also be compatible. And then now we discover that it's parity invariant as well. So P hat, P check as well. So all of this are compatible observables. And this is why we're going to use them to classify the states that we have written down over here already, right? So even though that we already know what they are, we will see. We can actually further classify them based on the symmetries of the Hamiltonian. As I'd like to emphasize in this course, symmetry is very important. Now, this observation that we made earlier was important because remember that because we know that this is proportional to some Hermit polynomial. Remember, this is h and 1 of square root omega x1, h and 2 square root omega x2, and h and 3 square root omega x3. Because of this, and then of course multiplied by the Gaussian. So because of this, because we know what we expect, and together with the fact that we know that these are compatible observables, in particular the j squared and j3, it means right away that we must be able to use the spherical harmonics to rewrite the product of these three Hermit polynomials to get then written in terms of spherical harmonics instead. Okay, so let me just write it down. So h and 1 square root omega x1, h and 2 square root omega x2, h and 3 square root omega x3 must be writable as the sum over some coefficients, right, which obviously depends on n1, n2, n3. But they must also depend on L and M in such a way that when I get R to the L times Y LM theta phi, when I superpose them accordingly, I must be able to get a sum like that. Okay, why? Because we know that the energy state now has the following decomposition, right? The energy eigenstate n equals to n1 plus n2 plus n3 must also be simultaneous eigenstates of L and M, and in fact there's also a parity. But we know that YLM itself transforms covariantly under parity. So this part is subsumed in L, but we will use this parity property very soon. So semicolon. So and because of that, the degeneracy we will see is basically captured by this superposition over YLM. Any questions for me? I think we should take a break, and then after the break we'll come back to figure out exactly how do we enumerate what are the terms that you will get, right? Exactly what are the terms you will get. And again, the clue will be coming down to this observation that we made, and the fact that each energy level is just degenerate. And all you need is just some n1, n2, n3, and they need to give you n. But there are many ways to do that. Okay, see you guys in 10 minutes. Yeah, so the key point is that HN1, HN2, HN3 is a polynomial, contains, that's a better way to say it, contains terms up to x1 to the 8th power, x2 to the bth power, x3 the C power such that A plus B plus C equals to N1 plus N2 plus N3. Okay, I'm not saying A1 is N1, B is N2, I'm not saying that. I'm just saying that the sum of these guys must be equal to that. Right. And why I read it in this way is remember that the definition of the definition of the spherical harmonics first came from defining them to be the homogeneous solutions of homogeneous polynomials of degree L. Right? So R, L, Y, L, M themselves are homogeneous polynomials of degree L. So that means they can be written as superposition of R to the L, Y, L, M from L equals to 0, 1, 2, all the way up to L max, given by N1 plus N2 plus N3. Okay. Now, this is also where the parity argument comes in. So let me write it down as well. Also, let's remember that under parity, so if you think about what parity means in terms of spherical harmonics, remember that the Gaussian is just invariant, right? It's R squared, X squared. So that doesn't it's just invariant. So what changes sign, you can tell, is that the derivative and the x1, derivative and x2, derivative and x3. So when you change sign, you can see right away that what will happen is that x, n1, n2, n3 would actually go to minus x, n1, n2, n3, which is, in fact, just by reading off the derivatives, it will go like minus 1 for the n1 plus n2 plus n3 times of the untransformed or the original wave function, right? So again, the derivative is odd under parity, so is the coordinate. So everyone would just transform, would just pick up a minus sign. Everybody will pick up a minus sign, and since you have that number of minus signs, that's how it goes. Okay? But in terms of the YLM, right? So remember, we just figured out that you can write it as a superposition of these guys times a Gaussian. How does this guy transform? So of course, R doesn't do anything, but because it's a distance. But what will happen is that when you do a parity transformation, theta will go to pi minus theta, and phi will go to phi plus pi. Okay, so if you need a diagram to see this, just draw the coordinate system, right? So this is 1, this is 2, this is 3, and say theta is this angle, and this is phi. Okay, so parity means what? You get from x to minus x. So if this is x, minus x is somewhere on the other side. Okay. So if you orient yourself this way, x is going this way, x is going that way. So phi will just be, you flip it over there, and phi will just be basically, yeah, it's hard to draw. Anyway, this will be phi plus pi, right? Because you're just going on the other side. But this angle here, the angle that minus x mixed with the vertical axis, the third axis, is in fact the same magnitude as theta, but because of our coordinate system, we will call that pi minus theta, right? is because of the way we define the spherical coordinates. We always define it with respect to the positive 3-axis. So this part is pi minus theta. Okay, so in case you're wondering where this comes from, I think this is fairly intuitive, right? I think one way to think about this one is just project it on the x on the 1, 2 plane, and so if x is going one way, then minus x must be going the other way. So you just add pi to it. This part, I think, takes a bit of work to think about, right? But just remember that the angle is always measured with respect to the positive third axis. And so even though the magnitude is the same, right, but it's measured with respect to the negative axis. So therefore, you want the larger angle, which is pi minus theta. But what is that? This is in fact, if you remember, just given by minus 1 to the L of the original YLM. Okay, and the easiest way to remember is in fact to remember that this guy, the whole object here, RL, YLM, remember the whole object here is nothing but a homogeneous polynomial of degree L. So when you flip x going to minus x, then all you're doing is exactly taking all the x's here and then flipping it by a minus sign, right? And so that's why it picks up minus 1 to the L. So what it tells you is that if you are looking at a particular, mode, the parity transformation properties had better be consistent with these two facts. Okay. Now, it doesn't mean that L must be equal to n1 plus n2 plus n3, right? Because this is minus 1. So these integers, that's an integer and this is an integer. These integers need not be equal because it's minus 1. So minus 1 to the 3rd power is the same as minus 1 to the 7th power, right? As long as they differ by an even number, right? As long as they differ by an even number, I will not in fact be able to tell in terms of the minus sign. Okay. And so in fact that's how we're going to write it. Remember the energy levels is given by omega times n plus 3 over 2. Okay, in 3D. Okay, and n is given by the sum of n1, n2, and 3, but it's only one number, so we may as well replace it with n. But now we discovered that. Sorry, I should call this 2s. Okay, so now we are going to replace it instead by omega times 2s plus L plus 3 over 2. Because now we discovered that we can use this fact that we have compatible observables given by the angular momentum operators and parity to let us know that that n can only differ by L, the harmonic number, by an even number. And this in fact, because this number has to be positive, it means that S can be 0, 1, 2, and so on, but the bound is a bound, right? For a fixed n, this cannot be bigger than that. But for a fixed L, S itself can run over the integers, the positive integers. Okay. So that's the energy level. And so I will let you guys figure out what would be the radial mode functions. So you will now, instead of writing these guys down, you will now write down x of n, which is this label n, L, and m, okay? And let me also remind you that there's an additional label m. This actually is a consequence of rotational symmetry. And remember that rotational symmetry, we discussed in a very general way, implies degeneracy in in M. Degeneracy in M. And M, of course, runs from minus L to L, right? Remember, we had this very general discussion. Whenever your Hamiltonian is, or any observable, is rotationally invariant, then the spectrum is necessarily, for a fixed L, is necessarily degenerate in M, right? It could depend on L, but it cannot depend on M, right? If it just depends on M, it means that your operator most definitely is not rotationally invariant. Now, I will let you guys figure out in the homework what the radial mode function will look like. So this will be the RLN of some radial function times YLM times the Gaussian e to the minus omega over 2 x squared, and then this will give you this energy level. So I'll let you guys figure out what is in fact the correct, what is the correct radial mode function. Okay. It's a bunch of again, it's a bunch of polynomials. I forgot to look up whether it has a name to it, but you will find that it depends. It comes down to some hypergeometric function. 1F1, I think. Yeah, I guess one more thing is that I shouldn't write this as R to the L, but rather I should just say that it's some radial, some function of R. Right, this is R and L of R, something like that. I think that's a more accurate way to put it. But you will solve for that. And one check, so I should mention, the one check that we will have is that you can try to write it down for a given n. You can try to write down what are all the possible wave functions for a given n. One check that you can have is how many, right? How many are there? Yeah, how many? And turns out that there's an argument that I think is in Weinberg, but you can see already what's going to happen is that you just basically count how many YLMs there are, right? So there's L equals to 0, that's 1. L equals to 1, there are 2L plus 1, that is I'm sorry. Remember that for a fixed n, L can only jump by 2, right? So remember, for a fixed n, L can only jump by 2. So I can only do L equals to 0, then I have to do 2, and then you get 2L plus 1. L equals to 4, I get 2L plus 4, and so on, right? Up to L equals to n minus 2s, however large my s is, okay? So, actually, sorry, until n, the floor of n, right? until either L equals to n or the floor of n. The floor of n. I mean the following. So, how do I write that down? So, n minus 1, I think. Not floor, but n minus 1. Depending on whether it's odd or even, that's what I want to say. This will give you either 2n plus 1 or 2n minus 1 plus 1. Okay. Sorry, I'm going to write it properly. So this is clearly for L even, right? So let me back up a little bit. We're going to split it up into two cases. So for, let's say n even, that's a better way to split it up. L can be 0, so that's one state. L can be 2, that is 2L plus 1, that's 4 plus 1, 5, and so on until you reach n. Okay, so this will be 2n plus 1, and we can sum up how many there are, right? So this is actually just sum from S, for S equals to 0 to n over 2 times 4s plus 1. Okay, why 4? Because it's 2L plus 1, but L is 2S. Okay, and this is just a arithmetic series, so I won't do it for you. Is it arithmetic or geometric? Some series that I won't do for you, but it's basically n plus 1, n plus 2 divided by 2. Right? It's a sum that you can do. And just from making this count, okay, just from making. So the tricky part, which I screwed up just now, was that I need to split between even and odd n. But for the homework, in fact, you will show that even for odd n, what would you do? You will start from L equals to 1, right? Because if this is odd, L can only differ from it by 2, so you've got to start from 1, otherwise you will not be able to hit, otherwise you'll not be able to hit n. Okay? Otherwise so you will get this sequence from L all the way to n, and then again L equals to 1 is 2 times 1 times plus 1. That's how many states there are here, all the way to 2n plus 1 states over here. And you will be able to count that this guy is exactly the same as this. Okay, so once you know how to do the sum, I claim that this actually is very simple as well. Right? You'll be able to figure it out. You'll be able to figure it out quite easily. Even though the counting, the intermediate steps of counting are different, the key point is that this is how much degeneracy there is. And this is a consequence of, as you can see, a consequence of both spherical symmetry and parity invariance, right? How many states there are here, you have to use both of these symmetries to tell you. Okay? Any questions for me? Yeah.
So how do you write n equal to minus L?
N equals to minus L. Where did I do that?
Symmetries imply dependence.
Where?
Okay.
M. This is M. This M, right? Did I use an M somewhere else? But yeah, M goes from minus L to L, right? Remember? So it runs over these values, minus L to L. Is that a question? Yeah, now N. Specifically, the report is about what is decoherence, right? The physics behind it. So the density matrix is only the beginning, right? You have to tell me about interactions between the quantum system you're looking at and the environment, and what about that gives you decoherence, right? What does it mean when we say that decoherence has taken place? So unfortunately, that part I have not seen a very thorough discussion yet. So yeah, I have to say, this is why I give you guys a midterm and a final, right? Because the last time I gave this also, people didn't do so well because they didn't really get to the point. And even if you get to the point, they don't spend a lot of time talking about it, right? And let me remind you, you had two months, more than 2 months actually, to talk about it. So you have another month before you turn in your final report. So I do hope to see a substantial improvement when you turn in your final report, right? Remember, the key point is to tell me in a basic way what is decoherence, not about the measurement problem, but tell me in a down-to-earth way, what does the decoherence mean? And very often, what might help is to pick up a simple example, right? There are models where people use to investigate the phenomenon of decoherence, right? Whether it's the qubits in quantum computing or there are other models as well. So I think, especially if you're learning something for the first time, one trick is to, in fact, instead of focusing on the general discussion, see whether some of these papers talk about, they give you simple examples, right? And you can start from there. That would be my suggestion. If you have trouble understanding the general case, pick up a small example and see from there what happens, right? Because I see a lot of people, when they are confused, at least that's a strong sense I got from reading your reports. When you're confused and you just have to turn in a report, what do you end up doing? You just copy the equation from the papers you read and just throw it on your report. And you sometimes don't even explain to me what the symbols mean, right? And I know that because I see the same equation over and over and over again, because I know you guys read from the same papers, right? So you throw the same equation there, you don't explain to me the symbols, sometimes you even copy the symbols wrongly. Or you copy the right symbols, but you don't explain to me what those symbols mean properly, right? That is right now is a major problem that I see in your reports. There's a reason why I do this, because my past experience is that people don't take the report as seriously as I would like to see. So I hope, once you get this feedback, we give you some impetus to. You still have another month or so to try to improve on it substantially. But it's very important. I think I said it already at the beginning of the semester. In graduate school, you'll discover it's extremely important to be able to teach yourself things. A lot of things that I know as a theoretical physicist, I know it through my own learning, right? Part of the reason is because academia can be a very competitive place. And so you may have a very busy advisor, There are other reasons that can happen, but you end up very often with some concrete goal that your supervisor gives you. But the details, you have to work it out yourself, right? And how do you figure out what to go, where to go, what to learn? These are very extraordinarily important skills to have. Otherwise, you will not survive as a researcher. If you need your, whoever is your advisor to guide you on every tiny little step, it's very, very difficult to survive in an increasingly competitive academia. Right? So this is my honest advice to you guys. Anyway, so yeah, this is I hope you take it as a experience to gain some independence in teaching yourself some things. Okay, so like I said, I want to do some discussion of density matrices before I return to the topic of angular momentum again. So what are density operators or density matrices? So the key conceptual point is that there are sometimes you have not only you have to deal with not only quantum uncertainty, which is inherent in the formalism of quantum mechanics itself. We have to also deal with statistical uncertainty. So what does that mean? So for example, if you took a statistical mechanics course, this is something that should be explained clearly to you, right? So, but as an example, even if you're in a closed room, right? Of course, we're not in a closed room because the window is open. Let's say you put yourself in a box, and the box is completely tight, but there's still, Avogadro's number of air molecules in the room, right? Otherwise, you're dead. You can't breathe. So there's air. There's lots of degrees of freedom that interacts with whatever thing you're doing in the box, right? Maybe you're doing an experiment. Maybe you're doing whatever it is you're doing. So the description of the whole thing, the whole system inside the box is necessarily going to be very complicated. And so very often the best we can do is to deal with this uncertainty in the statistical sense. In the sense that we are not, because we are not able to capture the dynamics of everybody, we try to only look at it at the level of the gross features. In statistical mechanics, you care about the temperature, you care about pressure, and so on. These are gross properties, properties that occur on a macroscopic scale, right? In fact, I should add that sometimes, in fact, we discover that even if you can account for all the degrees of freedom in your room, in your closed system, there are in fact gross features that emerge that you wouldn't have otherwise discovered if you didn't try to zoom out a bit, right? So in fact, goes both ways. We do statistical mechanics partly because we just don't have the computational power to deal with every single thing that is happening. But sometimes we realize we don't have to. In fact, if we did that, sometimes we discover that you miss, I think in English the phrase is, you miss the forest for the trees, right? So you're so hung up on the details that you lose sight of the gross features, right? So it can happen both ways as well. This is also related to this famous phrase that the Nobel laureate Phil Anderson likes to say, right? More is different. Why he says that is exactly because of the latter point that I was making. That it's very often the case that when you zoom out and you try to study systems on a coarse-grained level, when the zoomed out level, then you discover new features that you otherwise wouldn't have discovered if you only focused on the microscopic, on the tiniest features, right? So that's why he says more is different. But in any case, whether or not is it due to your inability to deal with the microscopic, there will be, once you do that, once you coarse-grain things, there will be some statistical uncertainty, not due to the quantum mechanical nature of the underlying way the world works, but uncertainty due to just incomplete knowledge. Okay, so this is just due to incomplete knowledge. So the simplest case that this happens is that if you have states, which I'm just going to label as psi 1, psi 2, and so on, and you only know with some probability that your system, let's say you do an experiment, but because in this closed box, but because the experiment interacts with the air molecules in the box, and maybe there's some temperature going on, maybe there's a fan blowing or whatever it is, right? So because of all this uncertainty that you cannot model accurately, you cannot say for sure now which state your system is in, because you cannot prepare it exactly in one state or the other. But what you can do is you can try to model what's the probability that you can find it in this state. So it's, let's say P1. What's the probability 1 that you can find it in state 1, probability 2 that you can find it in state 2, and so on. And of course, the only condition is that the sum of the probabilities must give you 1. So let's say this is what it means to be statistical, to treat things at a statistical level. Remember, this is not quantum mechanics anymore, right? At least the probabilities I'm assigning. I'm just saying that I don't know how to do this in a first principles point of view, but I don't want to. I just want to be able to say that I want to set up a formalism that encodes what I just said, that I can find my states to be in one of these n states with these probabilities. So what does that mean? That's a heuristic statement. What it means is that if I take the expectation value of some observable, I also want to average over the statistical possibility. Right, so this, I emphasize because this is not the same as just the quantum expectation value that we have seen before. The quantum expectation value, remember, is just you take one quantum state and you calculate the expectation value. And this you can think of as a quantum average. Right? Why? Because you can now do the experiment over and over and over again, and whatever outcome you can get from here will be basically, whatever outcome you can get from measuring O is basically given by this calculation. If you have a pure state, meaning you have a state where you know precisely what it is, okay, then you set it up, you make the same experiment 10,000 times, 1 billion times, and then you average the outcomes of that. Then that is the answer. The average of that will be this answer. But here, this expectation value, on the other hand, has to take into account not just this quantum expectation value. Quantum mechanics still works. So I have to take that into account, but also this statement that I was making in a heuristic way. What do I mean to say this guy has probability P1, probability P2, and so on? So what I mean is, in a precise way, is that when I take the expectation value, I also have to do it in a statistical sense. And that means I have to now sum over the expectation value, the quantum expectation value of O with respect to all the states I think I can find my quantum system in, but now weighted by the statistical probabilities that I'm assigning to these states. So this is statistical. Right? There's nothing quantum about this as it stands. What is quantum is this guy is quantum. Right? And so, like I said, this is the quantum average. But now the quantum average also has to be weighted by my incomplete knowledge about exactly what my system is doing. And because of that, I have to assign an additional probability Pi. Okay? And that is the basis of what we mean by statistical uncertainty. Okay, that is what I mean by this guy here. Okay, now as far as formalism is concerned, it turns out that to do this, you can write this as the trace of your operator with something called the density matrix. Okay, and this is what I want to talk about. So in the, let's say, so remember that even in this case, there's an issue of whether you're doing the calculation in the Heisenberg picture or the Schrodinger picture. So for now, this is just all in the Schrodinger picture, okay? And so then the density matrix, as we'll see, depends on time. Okay? And then later on we'll see what happens if you do it in the Heisenberg picture. But let's do this first. So why, the first question to answer is, how did I jump from here to this, and what is rho? Rho in particular is basically just the sum of these probability multiplied by the Cat-Bra projection operator, psi I, okay, sum over I. And let me emphasize also that I do not assume are not necessarily orthogonal. Okay. They're just some states. Like I said, we don't know what they are, right? We had to deal with them in a statistical sense. So I'm just going to write them all out, and by some means, I have to figure out what is the relative probability that I can find my expectation value, basically. because these states evolve with time, right? They still have to obey quantum mechanics. So that is why this density matrix obeys the time evolution, right? So this guy necessarily, these guys necessarily depend on time, because they're describing a physical system. They still have to obey quantum mechanics. They still have to obey the Schrodinger equation. Okay, so let's first understand this step. Okay, so it's not too difficult. So you just sum over the states that you're weighing the probabilities over. But of course, you can also use the completeness relation. So you can choose any orthonormal basis. So let me just write it down. Any orthonormal basis. And what do I have here? Psi I, N, O. I'm just going to suppress the Schrodinger subscript. Okay. So psi I, N, so that's just the completeness relation. And then N prime, psi I. What I'm going to do, so again, we have two completeness relations. And what I'm going to do is I'm just going to rearrange them. So I'm going to say that this is N, sum over I, sum over N and N prime, and then Pi, and I'm going to rearrange it in the following way. Right? I'm going to say that this is just, move this over here, I'm going to say that this is psi I, N prime, psi I, N, that's this guy. And then we have this guy here, N, O, N prime. Okay? All I've done is just rearrange things a little bit. Because we started from the completeness relation, and now I rearrange it in this way. And what you see is that NN is just nothing but the identity, right? So I can actually lose that part. I could have just written this as psi O N prime. But anyway, now what we see is N prime. I'm going to pull the bra out. I'm going to pull the cat out like that. Okay. But what's inside here is now the sum over the probabilities, Pi, and then we get psi I, right? So this guy is this guy, and then I've gotten rid of the sum over N, so this is just psi I acting on O. Okay? And so if I think of this as one object, this is an operator acting on O, and the sum over N prime is just a trace. Trace exactly means you sum over the diagonal components in an orthonormal basis. Doesn't matter what orthonormal basis. We showed a while ago, we showed that as long as you choose an orthonormal basis, it does not matter what basis that is. But anyway, so this is trace, and now you have an operator. If you call this your row, actually I should just call it row, because in my convention, row hat is a matrix, but now right now it's not a matrix yet. So this is now row of T, and then multiplied by O. And that's exactly what I claim. So it's just a few short steps, but basically it allows you to rephrase your statistical and quantum average as a trace, okay, and involving a density operator and whatever operator that you want to find out the average of. And that why that is useful is because once you know rho, then you can use any O you want, right? So this this object, you might think that, oh, I have to calculate this average for all possible operators before I can know what it is. But no, allowing you to write it this way means that once you know rho, then you have to do the calculation just once. Just multiply it by O, and you take the trace. Okay, so this is O independent, right? So it's kind of universal. It's a universal object that you can use for your given system to describe this statistical and quantum average. Okay. So let me just do one more thing before I let you guys go. Okay. So the one more thing is rho depends on time, so it evolves in time. Because the cat and the brass evolve in time. Okay, so let's figure out now, how does that guy evolve in time? So we take I and then take dot of rho, and we recognize that this means I'm taking the derivative. So what is rho? Remember, it's just the sum of the probabilities, which I'm assuming do not depend on time. This means that I do I dt acting on psi I, and then plus psi I, and then I dt acting on psi I. Okay? There's two things I need to differentiate. One's the cat and one's the bra. Now remember that the cat is just a Schrodinger equation. Right? So I can immediately write down that this is pi, and then Hamiltonian times psi I. This guy, on the other hand, I can write this as basically minus I times with the minus sign here. Okay, because, and why do I do that? Because this is just a compact, this is just an adjoint of this guy here. So now I can say that this is now minus psi I, and then the adjoint of h psi I. Okay, so altogether, you can pull it out and you realize that this is actually just h times rho pi psi I, and then here you get psi I cat, psi I bra multiplied by h. So you get h rho minus rho h, which is of course nothing but the commutator of h rho. Okay. So this looks almost like, it's a little bit confusing. Okay, if you remember we talked about the Heisenberg picture, this looks almost like the Heisenberg equation solution, but I have to warn you, it's not quite the same because of the sign difference. You will discover there's a sign difference that makes it not the same thing. But this is an important equation. Right? It tells you that the Schrodinger picture Heisenberg density operator obeys this equation, and of course this is because the cats and brass evolve. So you may have, so let me finish with one last statement. You may wonder, why do I let P not depend on time? So the reason is because your quantum mechanics will determine its evolution, right? So Pi, when we say is time independent, is basically the probability that you can find is to be associated with the probability at some given time, right? The time evolution, you can think about it that way. And then the time evolution will then take care of what the quantum average how that part would evolve with time, right? Otherwise, what you end up with is that you also have to tell me how does the probability, what kind of dynamics the probabilities would have themselves, right? It will just make the problem even more complicated. It might happen, but then you will have to tell me, in that case, what is going on with the P, right? But let me just say, for now, what we're saying is basically, we think we know what the probabilities, statistical probabilities at a given time,